Hello, good morning everyone. I am K. Narsimurthy. I am presently working as an assistant professor in Government First Grade Women's College, Tumkur. I have presented 38 videos so far. In my 30 videos covers the electrostatics and the magnetostatics. So from the 31st video I started the magnetic materials, and from the 3 videos back I have started a new chapter which is called Maxwell's equation. In my last 2 videos, I have derived 3 important Maxwell's equations. This Maxwell tells that these electric and magnetic fields are no way separate entities. They coexist. The electric field and the magnetic field coexist. And now they are the 2 aspects of the same topic, which is called electromagnetism. So the 4 important laws of electrostatics and the magnetostatics, like Gauss law, Ampere's law, Faraday's law, and these laws have been expressed in terms of 4 different equations, and these equations are called Maxwell's equations. Maxwell's gave a beautiful 4 equations by just modifying these 4 laws of electrostatics and magnetostatics. The behavior of electric field and magnetic field is governed by these 4 fundamental laws of Maxwell's. These 4 Maxwell's equations are as important as Newton's laws in the mechanics. Now I have done the 3 important Maxwell's equations. I have derived the 3 Maxwell's equation, and now I am looking for the 4th Maxwell's equation. Right, today I am going to derive the 4th Maxwell equation, and that was the curl of H is equal to J plus dou D by dou T, where H is the magnetizing force and J is the current density and D is the displacement vector. Okay, right. So this 4th Maxwell equation we are going to derive from the Ampere's law. Now you know all about this Ampere's law. I have discussed in the previous video about this Ampere's law. Okay, so Ampere's law says that line integral of magnetic induction, means magnetic induction over a closed path, is equal to mu naught times the net current enclosed in that closed path. Okay, so that means to say magnetic flux over a closed path, that means to say line integral of B dot dl is what the magnetic flux over a closed path is equal to mu naught times the net current enclosed in that closed path, mu naught times the net current, mu naught times I. So line integral of B dot dl, which is the magnetic flux over a closed path, is equal to mu naught times the net current enclosed in that closed path. So this is the Ampere circuit law. Let us call it as an equation 1. Alright. Now we know the total current I is the surface integral of J dot ds. So we know what is J is. J is the current density, current per unit area per unit time. If J is the current per unit area, if I multiply that with a very small area ds, so current per unit area into small area will use the current in that small area ds. If I want the current in a one complete surface, so then I have to integrate this J dot ds over a complete surface. So it will be the surface integral of J dot ds. Right, so I got the total current. Now I can substitute this total current equation, which is surface integral of J dot ds, in that equation 1. Now our equation 1 becomes line integral of B dot dl is equal to mu naught times the surface integral of J dot ds, which I expressed as current. Okay, I have substituted for the current in the equation 1 as surface integral of J dot ds. I got equation number 2. Now after getting equation number 2, now I will go with the Stokes theorem. Stokes theorem, which converts line integral into a surface integral. Only thing is we have to do a curl of a vector. Line integral of a vector is equal to surface integral of curl of that vector. So line integral of B dot dl is equal to surface integral of curl of B into ds. Okay. Now this equation 3 means the Stokes theorem. I am going to substitute in the equation 2. So equation 2 becomes, instead of line integral B dot dl, I am substituting surface integral of curl of B ds. So surface integral of curl of B ds is equal to I, mu naught times I is surface integral of J dot ds. Okay. So I have substituted this Stokes theorem in the equation 2. I got this equation. Now what I am doing is, both sides I have surface integral. Now I can equate the quantities inside the surface integral in both sides. So left hand side the quantity is curl of B, and the right hand side the quantity is mu naught J. So I am not doing anything to the equation. I am just equating the quantities which are inside the surface integral, because I have surface integral both sides, both in the left hand side as well as in the right hand side. So I can equate the quantities very easily. So curl of B is equal to mu naught J, which I am calling it as equation number 4. Right. Now this equation, the equation number 4, which I have derived from the Ampere's law, curl of B is mu naught J. This is consistent for a steady current in a closed path. This equation is okay. This equation is consistent for a steady current, but that in a closed path. And it is found that it is inconsistent with the equation of continuity. Students, I have derived an equation of continuity in the beginning of this chapter itself. Okay. So let us see how this equation is inconsistent with the equation of continuity. Okay. Right. Let us take divergence on both sides of equation 4. So this is the equation 4 which I am getting. If I take divergence on both sides, divergence of curl of B is equal to mu naught times divergence of J, which is going to be 0. Why it is 0? Because you know that divergence of curl of any vector is going to be 0. Okay. You cannot do a divergence and the curl for a vector. Okay. Divergence means a vector lines going out. Curl means it is a swirling, it is a rotation. So any vector cannot have both the quantities. So it will be 0. It cannot have a non-zero value. So divergence of curl is 0. Therefore, this left hand side 0 means the right hand side would be 0. So div dot J will be equal to 0. Anyway, mu naught is not 0. Mu naught is a constant. We know it's a permeability of free space. That cannot be 0. Therefore, div dot J will be equal to 0. I got this divergence of J equals to 0. So this equation, I know the equation of continuity, which clearly tells us that the divergence of J is not 0. It is supposed to be minus dou rho by dou t. So this equation is in accordance with the law of conservation of energy. We know the equation of continuity, which is div dot J is equal to minus dou rho by dou t, is in accordance with the law of conservation of energy. Okay, it is derived from the law of conservation of energy. It shows the law of conservation of energy. Therefore, this is not wrong. The equation of continuity is wrong. But where is wrong? Where we are going wrong? But there is something wrong in the equation number 5. Div dot J cannot be 0. There is something wrong with the equation 5. Or if we go back, there will be something wrong in the equation 4. So there is something wrong in the equation 4, because equation 4 is not in the consistent with the equation of continuity. It is inconsistent with the equation of continuity. So now it clearly shows that the equation 4 is in inconsistence with the equation of continuity, because if I take a divergence, now finally div dot J becomes 0, but that will not happen according to the equation of continuity. The div dot J will be minus dou rho by dou t. So our basic equation number 4 is inconsistent with the equation of continuity. It is violating the law of conservation of energy. The equation number 4 is violating the law of conservation of energy. Therefore, there is something wrong with the equation number 4. So that is why the Maxwell's identified this inconsistency in the Ampere's law and suggested a new term. Maxwell suggested a new term for the equation 4. He suggested displacement current density. Instead of conduction current density, the Maxwell suggested a displacement current density, which we call it as JD. Okay, we know what is displacement current is. We know what is displacement vector is. Displacement current density is a dou d by dou t. It's rate of change of displacement vector. So we have to substitute some quantity here to make this law consistent with the law of conservation of energy, and that quantity was identified by the Maxwell, and he suggested it has to be a displacement current density. So curl of B is equal to mu naught times J plus JD. So earlier I was having only mu naught J in the equation 4. Now the equation 4 is modified. Yeah, now we are adding JD for the equation 4. So we have J plus JD instead of only J. Now let us call it as equation 6. Now take the divergence. Now this divergence of curl of B is equal to mu naught times divergence of J plus divergence of JD is equal to 0. We know divergence of curl of a vector is 0. Now it is not simply divergence of G which is equal to 0. Divergence of J plus divergence of JD is what equals to 0. Now divergence of J is equal to minus divergence of JD. So divergence of J, which is from the equation of continuity, it is minus dou rho by dou t, which is equal to minus divergence of JD. Okay. Therefore, equation of continuity is what the equation 7. So we have substituted equation of continuity and we have got this equation. Now the Maxwell's first equation we have derived in the last video. That was divergence of D is equal to 0. Sorry, is equal to rho. That I am substituting in the equation. So divergence of JD, so equation 7 becomes, so divergence of JD is equal to dou by dou t of, instead of rho I am substituting divergence of D. So it is dou by dou t of divergence of t. So I am modifying the equation 7. I am substituting divergence of displacement vector as a rho, as a charge density in the equation 7. So I have got a modified equation 7. Now after that, divergence of JD is equal to divergence of dou d by dou t. I am writing divergence outside. So both side I have divergence. I can equate the quantities very easily. So JD is equal to dou d by dou t, which I am calling it as equation number 8. Okay. Now on substituting equation 8 in equation 6, go back and see what is equation 6. It is curl of B is equal to mu naught J plus JD. So for JD I am substituting dou d by dou t. So therefore the equation number 6 becomes curl of B is equal to mu naught times J plus, for JD I am substituting dou d by dou t. Alright. Now curl of B, I am dividing the mu naught. Mu naught I am dividing to the left hand side denominator. So curl of B by mu naught is equal to J plus dou d by dou t. I know the B by mu naught. The quantity B by mu naught is the H, which is the magnetizing force. So curl of H is equal to J plus dou d by dou t. Now because I know B is a magnetic field is equal to mu naught H. So we know mu naught B by mu naught is H. So this curl of H is equal to J plus dou d by dou t is the Maxwell's fourth equation in the differential form. So I have derived the Maxwell's fourth equation. Suppose in the exam if they ask you to derive a Maxwell equation, it is enough if you stop at this level. You don't need to derive an integral form of Maxwell's equation if in the exam. Okay, it is for your reference, it is for your knowledge. I am continuing and I am getting an equation for the integral form of the Maxwell's equation. It is enough if you stop at this stage in the exam. Okay, let us move further and do the integration with the I'll take surface integral on both sides. So surface integral of curl of H ds is equal to surface integral of J plus dou d by dou t dot ds. Now I am splitting the surface integral on right hand side for the two quantities. Surface integral of J dot ds plus the surface integral of dou d by dou t dot ds. Okay, that's an equation number 9. And I know from the Stokes theorem, which converts line integral into surface integral. A line integral of a vector is equal to a surface integral of curl of a vector. So line integral of h dot dl is equal to surface integral of curl of h into ds. So I am substituting in equation 9 this Stokes theorem. So instead of surface integral, I am substituting line integral of h dot dl, which is equal to surface integral of j dot ds plus surface integral of dou d by dou t dot ds. That's what I have substituted. Now, still I need to continue one more step here. The surface integral of j ds is what actually the current. Current is the surface integral of j dot ds because j is the current density. Okay, current per unit area. If I multiply that with the area, I will get a current. So this is the current enclosed. Current enclosed in a surface H S, which encloses a volume V, plus surface integral of dou d by dou t dot ds. This is what the integral form of Maxwell's fourth equation. I have derived the differential form and I further continued. I integrated this with the surface and I got this integral form of Maxwell's fourth equation. Okay, so it is enough if you stop at the differential form itself. Now, so I need to give explanation about the equation which I got finally, the physical significance of this. This equation represents generalized form of Ampere's law modified by Maxwell's. This is nothing but an Ampere's law, but little bit modification is there. Why we did a modification? The equation 4 which we are getting, curl of B is equal to mu naught J, is not in accordance with the law of equation of continuity. That means it is inconsistent with the law of conservation of energy. That is why Maxwell did some correction for that equation. Maxwell's added some quantity for that equation, and that quantity was JD. There is some current along with this conduction current. There is some current which exists. That is what the displacement current is. Displacement current will also produce a magnetic field. It is not a motion of charges just like a conduction current, but it produces a magnetic field how that conduction current produces. Okay, so this equation is a generalized form of Ampere's law modified by Maxwell. Okay, this law predicts that the magnetic field can be produced by conduction current as well as displacement current. So now this law is in accordance with the law of conservation of energy. It is consistent with the law of conservation of energy. Therefore, we can say that this displacement current will also produce a magnetic field. Just like how conduction current produces a magnetic field, in the same way the displacement current will also produce a magnetic field. Okay, so these are the two conclusions. These are the two significance we can say for the Maxwell fourth equation. So now I have finished all the four Maxwell's equations, though they are simple, but a lot of mathematical steps involved. That's it. Finally, we are interpreting physically. Final step, the final equation, we are interpreting it physically, and we are looking for the physical significance of that equation. That is what actually important in the physics. Okay, so anybody can derive a Maxwell's equation so simply with the mathematical steps. Final conclusion, final physical significance is what more important than just doing a simple derivation. Okay, now the four derivations are finished. So in an exam they can ask you two derivations at least for one complete question. For 1 8 marks question they can ask you for any two Maxwell's equation. They will specifically mention the equation to be derived in the exam. Okay, so you all practice all the four Maxwell's equation. Any two equations can be asked in the exam. Okay, right. So these are some of the books which I referred. You refer any good electromagnetism book. A lot of electromagnetism books are available. Even the College Physics by Sundarajan is also a very good book. And the Griffiths, the electromagnetic waves, electrodynamics by Griffiths is one of the very good book but tough book. And these two are like a syllabus. These two are like a book which is written exactly onto the syllabus. Okay, like a textbook. These two are like a textbook. So you also refer this. Okay, you will understand the four different Maxwell's equation better. Thank you very much.